So in this example, the function is actually given to you. So let's first start by defining our variables. So when you reread the problem, it says that t is the number of months and that p is the population of insects. So I always recommend writing down what your variables represent. So t is the number of months and p is going to be the number of insects. So for part A, it asks how many insects were initially discovered. So if we're looking at when the insects were initially discovered, then we're really talking about when my time is equal to 0, at t equals 0. So this means that this problem is asking us essentially to put in t equals 0. In other words, you're finding p of 0. So if you put 0 in for t, you end up with 50 divided by 2, which would be 25. So there were 25 insects initially discovered. So remember the graphical meaning of this value. Really, if we're putting in 0 for x, or in this function, we're putting in 0 for t, then what we're really finding is the y-intercept. So the graphical meaning of this value, we can say that it's the y-intercept on this function's graph. You could also call it the p-intercept. So we'll say that 25 is the y-intercept, or you can call it the p-intercept, either one, on the graph. Moving on to part B. How long will it take the population to reach 300 insects? So focus on first what the question's asking. It's asking for how long it's going to take for this to happen. Look at your variables and decide if we're looking for how long it takes, are we solving for t, the number of months, or p, the number of insects? So if we're looking for how long, then essentially we want to solve for time, for t, the number of months. And then what's given to us, 300 insects, that's my population. So that's telling me that I need my p to equal 300. So that's just a substitution problem as well. Substitute 300 in for p, for population, and we get an equation to solve. 300 equals 50 plus 25t, all divided by 2 plus 0.01t. So to solve this equation, we'll multiply the denominator, 2 plus 0.01t. We'll multiply both sides by that denominator. So we'll end up with 300 times 2 plus 0.01t is equal to 50 plus 25t. And then you want to go ahead and distribute and combine like terms. So distributing your 300, we'll end up with 600 plus 3t equals 50 plus 25t. And then continue solving this equation. So subtracting your 50 gives us 550, and subtracting 3t gives us 22t. And then finally divide by 22. So we should get that t is equal to 25, and then attach the units. That would be 25 months, because t was measured in months. It'll take 25 months for the population to reach 300 insects. The last part of this problem, part C, is asking for what the largest population can be. What is the largest population that the protected area can contain? So you need to kind of think graphically for a second. If we're looking at t being the number of months and p being the population, we're wondering essentially, does this population just continue to grow, and continue growing upward? Or does the population level off as time goes by? So is it one where it's going to continue to grow, or is it going to level off? So really, you're trying to ask yourself the question, what is happening as time goes on, which is mathematically speaking the same as saying what's happening as t approaches infinity? What happens as the number of months gets bigger and bigger and bigger? So let's look at our function again. We have 50 plus 25t divided by 2 plus 0.01t. So what's happening as t gets infinitely big? Well, remember, if t is going to infinity, this is essentially the same as asking, what's the right behavior on our graph? What's happening as we move far to the right on our graph? So we're looking at the end behavior. This happens to be a rational function. So if the population does level off, that means we would have a horizontal asymptote. And we know that we can't figure out the horizontal asymptote until we analyze the degree of the numerator and the denominator. So the numerator is degree 1. The denominator is also degree 1. So that's going to tell us that we are going to divide our leading coefficients to determine what our horizontal asymptote is. So in this problem, this particular function, we know we're going to have a horizontal asymptote of y equals 25 divided by 0.01, which means we have a horizontal asymptote of y equals 2500. So now we can answer the question, what's happening as t goes to infinity, as time gets infinitely big? Well, the y values on my function, which are really my p values, the population, my p values are not getting infinitely big. My p values are approaching 2500 because that's the horizontal asymptote. This graph levels off. It grows and grows and grows, but it's still leveling off, approaching 2500. So what's the largest population that this area can contain? The answer is going to be 2500 insects, because that is the horizontal asymptote of this particular function.